First, I would like to discuss something about a real black hole. So this is a black hole, and this is the event horizon of a black hole. Now, if sound tries to escape from outside the event horizon, it can go forward against the gravitational pull of the black hole. However, if a light wave tries to escape the black hole from within the event horizon, it gets sucked in by the gravitation. So let's look at a small area of the event horizon for a moment. We'll zoom in, and we'll look at now at an analog of a black hole. In an analog of a black hole, we have fluid flowing in one direction. And we think of this as one small region of the event horizon. Now, we must create a situation where on one side of the event horizon, the fluid is flowing slowly. At the event horizon, the fluid is flowing at the speed of sound. And on the other side of the event horizon, the fluid is flowing faster than the speed of sound. Now let's consider a phonon, a sound wave, trying to travel against the flow. Well, if it's on this side, where the flow is slow, it can go forward. Whereas if it's created on this side, it will not be able to travel against the rapid flow, and it will fall inward. Now, it's interesting to consider the energy of these phonons. This is related to Hawking radiation, what I'm telling you about, which is a kind of radiation emitted by a black hole. So let's consider the energy of these phonons. As you'll see soon, we know the energy of a phonon in a fluid if the fluid is stationary. But now let's think about what happens if we're looking at a reference frame where the fluid is moving. So in the fluid reference frame, the fluid is moving this way and the phonon is moving this way. In the fluid reference frame, we know the energy of the phonon. Now look in the laboratory frame, which is moving in this direction. Since the fluid is moving in this direction, it's as if the laboratory is moving to the right relative to the fluid. And then we could perform some mathematical transformations, and we can find that the energy of the phonon in the laboratory frame is smaller than the energy of the phonon in the fluid frame. So if we now look at the excitation spectrum, which we know, this is a phonon region where the energy is linear in the momentum. That's like a phonon or a photon. In this region, this is the phonon part. And then it becomes parabolic as one considers shorter and shorter wavelengths, higher and higher momenta. So one can see that the excitation spectrum is the same phonons which are moving to the right or to the left. That means the energy of a phonon doesn't matter if the phonon is going to the right in the fluid or in the left in the fluid. However, if the fluid is moving, and now we're looking in the reference frame of the laboratory, first of all, we actually measure this excitation spectrum in the Weizmann Institute. Yeah. And so this really is the excitation spectrum of our quantum fluid, which I'll discuss soon, which we'll see soon. So if the fluid is now flowing, then that reduces the energy of these phonons which are trying to travel against the flow. And this is if the flow is a little bit less than the speed of sound. However, if the flow is greater than the speed of sound, then we see that the energies become negative. And this, we'll see that this creates the possibility to emit phonons without any input of energy, since it doesn't cost any energy to make them. Unfortunately, this also means that the fluid becomes unstable. The fluid becomes unstable, so we had to somehow overcome this instability in the fluid, to let the fluid flow faster than the speed of sound, even though there's sort of a law called the Landau critical velocity which says that one can't do that. But fortunately, in order to create the instability in the fluid, one needs an external source of momentum. One cannot just make the phonons, even though one doesn't need any energy to make the phonons, one needs a source of momentum, like a rough surface. So we made a situation with no rough surfaces, so there's no source of momentum to create these phonons, so the fluid could be stable. We did this in the following way. Let's say we had a potential which looks like this. And these are particles which are, you could think of these as classical particles which are just moving in this potential. Well, if the particles start up high, then they'll move into the potential and they'll get a large acceleration when they go through the potential, and then eventually go back up to the height where they started. And they will spend very little time in this region, in this minimum region, because they're moving very fast. So this is how we accelerate the gas. We have the atoms start up here, and they reach this point and get accelerated very rapidly. And here's what it looks like. So this is the cloud of atoms, and here's the region where this minimum is. And then there's another cloud on the other side of the atoms on this side of the minimum. And so we call this density inversion, because usually one would think that where there's a minimum, there should be the most atoms. But since we start the atoms up at the top, it actually turns out to be the opposite, that where there's a minimum, the atoms spend very little time in this region, and so we get this region with almost no atoms. So this is how we actually do the experiment. We start with the atoms in this region. We move this parabolic potential up here to the left, leaving this deep Gaussian potential at the same location. So this moves to the left, bringing the atoms to the minimum. Then they pour in and go over to the other side, as we see in this picture. Here's what it looks like when we adiabatically put the atoms into the minimum. They just sit in the minimum. And here's the picture that we saw before. And interestingly, this picture looks very similar to this picture, which is the case of a repulsive potential in between the atoms. So we see that a repulsive potential and an attractive potential look very similar, actually. So this symmetry, one can understand that the atoms have difficulty gaining energy. They can't gain energy to enter this barrier, but they also can't lose energy in order to sit in the minimum. So the way that we create this minimum, the way we apply the force to the atoms, is with a laser beam. So here's what the atoms look like when there's no minimum. The minimum is created by this laser beam, which is moving out of the screen. And due to the stark shift that this laser beam creates on the atoms, it can repel or attract the atoms. In the case of this talk, it attracts the atoms. Here's what the laboratory, the front end of our experiment looks like. The cold atoms are here. And here is what the optical system looks like. The atoms are at this location, and we have these two high numerical aperture lenses, like microscope objectives, that look at the atoms. We can take pictures of the atoms, and we can also apply forces to the atoms. This laser beam here is the laser beam that is the attractive potential for the atoms. Now, how can we look at the flow? And what we see is the fluid traveling fast, crossing the speed of sound, creating the sonic black hole. Here, this is a picture at a certain time. At a later time, this is the image that we get. So we see on the left side, there are more atoms at later times. So we start out with very few atoms on the left side. So later, there are more atoms on the left side. We know that atoms were flowing from left to right, as we imposed on the atoms to do. Furthermore, the atoms, in order to get from the left to the right, had to go through this region, the empty region in the middle. So they must have been going very fast. By the continuity equation, to go through a region with almost zero density, something must move very rapidly. Here are profiles of these images. So the blue image is at early times, and then the green image is at a later time. And we see that there are more atoms on the left side in the later image. So we could apply the continuity equation, assuming that all the flow is only in one direction, which we prove by these images that it's a good assumption. By assuming that all the flow is in one direction, we can find the velocity of the flow by comparing the images. So basically, we're just saying where we see that the flow is clearly going to the left, and we could write that down mathematically. So what we find is here's the velocity as a function of the position. So the red line is the velocity, or the potential minimum. The velocity gets very high. Now the black line is the speed of sound. There's good understanding in the world of these cold gases, and so we can just by looking at the density from the image, we know what the speed of sound must be at each point within this gas. The speed of sound is much lower than the speed of sound in air because these are very low density gases. So you can see here the speed of sound is less than 1 millimeter per second in the gas. Here's the black line is the speed of sound. Now we see that the red line, the flow speed, equals the speed of sound at this point here. So that's analogous to the event horizon of the black hole. Here's showing on the images where the event horizon is. The green line is the point where the speed exceeds the speed of sound. Now, in the future, one would want to use this system to measure Hawking radiation. So what is Hawking radiation? Let's say we create a phonon on the low speed, the side with low speed. It will be moving very slowly. It will be barely going faster than the speed of sound. Actually exits away from the event horizon here. It will start moving faster because the flow speed is very low in this region, so it will be moving at basically the speed of sound. So its wavelength will actually get longer. It starts out here with this very short wavelength, and then it will have a longer wavelength, because what's conserved as it moves is the frequency of the wave. Since the speed gets higher, here the wavelength will become longer. In this region, if this is the Hawking radiation, say reaching some distant observer, if you think of this as a real black hole, this is the photon, the light wave, which reaches Earth, say. When this photon, which reaches Earth, was actually near the event horizon, it had a very, very short wavelength. And this is actually physically interesting, because the wavelength, as one gets closer and closer to the event horizon, should really go to zero. And so studying these infinitely short length scales is interesting in itself. However, if the phonon is created on the other side of the event horizon, then it gets sucked into the black hole. It can't move forward against the fluid. Its wavelength still gets longer, but it has negative energy, as we learned. We learned that when the flow is faster than the speed of sound, the energy of this is negative. So this phonon is called the trapped phonon, and this phonon is called the escaping phonon. Now let's look at these phonons on the excitation spectrum. So here is in the supersonic regime, flow faster than the speed of sound. We said that that phonon has negative energy, whereas on the other side, the escaping phonon, the flow is less than the speed of sound. So all the energies are positive still, and so the phonon is at this point. So we can create one of these and one of these without any energy. So this phonon has a negative energy, and this phonon has a positive energy. So we can make a pair of phonons with zero total energy. And this is Hawking radiation. And this is a quantum effect, this production of this pair of phonons. And that's why we need the very cold quantum gas. The pictures I was showing you is at a temperature of around less than 10 nanokelvin. So it's a very, very cold gas. And so when all the atoms are in the same quantum state in the gas. It's a Bose-Einstein condensate, and so that's an example of a quantum gas. Now, if we want to see Hawking radiation, the creation of these pairs, we need a significant Hawking temperature. In other words, we need these phonons to have a short enough wavelength for us to see them. So we want a high Hawking temperature. We want these phonons to have a lot of energy and short wavelength. So the Hawking temperature, in the case of the analog black hole, is given by the gradients in the velocities. So in other words, the velocity starts smaller than the speed of sound and goes to larger than the speed of sound. That transition must occur on a very short length scale. That increases the Hawking temperature, and that decreases the wavelength of the Hawking radiation. So we can look at our experiment. This is our experimental results, where we see the speed of flow going well above the speed of sound here. These various curves are at different times. We look at the experiment. So from the slope of this curve, we can calculate what the Hawking temperature would be if in the future we can see Hawking radiation. And we find that the Hawking temperature will be around 0.3 nanokelvin, which is a very small Hawking temperature. If we can see if this is what the wavelength is of phonons with a temperature of 0.3 nanokelvin. This is our experiment. Its size is around 20 microns. That's the total size of this cloud. That corresponds to a wavelength. If the wavelength were 20 microns, then the temperature would be 2 nanokelvin. So if we want to have one wavelength across this gas, we would have to have 2 nanokelvin as our Hawking temperature. So we're an order of magnitude away from that. Our Hawking radiation would have a wavelength an order of magnitude larger than our entire sample. So we won't be able to see those sound waves. Well, if we want to see Hawking radiation, we'll need to decrease our wavelength of the Hawking radiation. So the way one can see Hawking radiation would be to look for correlations, to look for the fact that a pair is created. One should see a phonon on this side and a different phonon on the other side created simultaneously. Also, this space, the dark region where the flow velocity is very high, could actually be a laser resonator for Hawking radiation. That the Hawking radiation could resonate inside of this cavity. These are proposals in the literature for how one can observe Hawking radiation. So in conclusion, we've created a sonic black hole white hole pair. I didn't have time to discuss what the white hole was. The white hole is where the fluid actually goes slower on this side, where the fluid again slows down and is going slower than the speed of sound. That's called a white hole. So we made a sonic black hole white hole pair in a Bose-Einstein condensate in the cold quantum gas, which means we achieved supersonic flow of the gas. Our technique was we used the atoms seemed to be repulsed by the attractive potential, and that caused the high flow velocity. We saw that the flow field contains regions of positive and negative phonon energies, or we predict that. We didn't actually measure the phonons. But we still have to improve our system by an order of magnitude in order to actually observe Hawking radiation. Thanks.
Do